In this week's episode, I am talking to Dr. Phil Winder, who is author of the reinforcement learning book published by O'Reilly. He also runs Winder AI and Helix ML, which we'll hear about more in the episode. So Phil is an expert in reinforcement learning, machine learning in general, and has been doing AI since before it was cool. Hopefully you enjoy this episode. So before we started recording, we were just talking about the sort of trials and tribulations of model-based products and the training process, and whether you get kind of linear progress towards an outcome or a goal, or whether it's more nothing, 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 and then all of a sudden you get something fancy. So you've been into machine learning, AI, reinforcement learning since before it was cool. So that must be quite kind of interesting seeing how the market has shifted, and the thing that was presumably reasonably niche with only specialists involved now has everyone and their dog excited about it, and presumably kind of saying things that might not be entirely factually accurate about it.
Yeah. So maybe let me go back to the start and give you a bit of context to my background, because I think that helps with this discussion. So hi everyone, my name's Phil, if you haven't heard me already, and I started off as this isn't an AA anonymous thing. I started life as an electrical engineer. I did electronics at university, and at that point we were working in chips still. I was doing lots of signal processing that turned into data science effectively and machine learning, but it was all in chips. And so I was basically the last batch of people that just about programmed in assembly language in chips.
Oh, wow.
So when I started, that was there. Whilst I was there, it was moving to C, and kind of everyone was programming in C at that point. And that was like, sort of 2003, 2005, something like that. But yeah, and then very quickly I kind of moved out of chips into computers, and then did lots of software engineering and stuff, and found this whole other world. And around me, data science was emerging as a discipline. It was data mining at that point, but data science kind of was a better description for what it was, because it was an exploration of the data in order to do something with it. And then machine learning was kind of learning algorithms to make decisions based upon that data, and then reinforcement learning to explore environments proactively in order to learn models about that environment and learn to make decisions in that environment. And then finally, kind of AI came out of all of those, as in terms of the LLMs that we're kind of calling AI now. And they have a similar background. They're still trained upon a corpus of data. They're still a predictive model. They're attempting to predict words rather than decisions or anything like that. But it's still a predictive model. And therefore, all of the same things that I've been working on for the last 10, 15 years still apply. And yes, you're absolutely right. The interface of natural language has meant that everybody is now able to take advantage of ML and AI just simply by talking to it and chatting with it and asking it to do stuff. And that has meant that the scope of who ML touches has increased massively, and therefore the sort of quote market has increased massively. So it's been interesting to watch that from the outside.
What do you think are the kind of biggest misunderstandings that people have about ML-based projects compared to traditional software engineering?
Yeah, so we were chatting about this just before, because I was bitching and moaning. I think one of the biggest problems is that traditional software engineering, like any engineering, is quite prescriptive. Once you've learnt the patterns and the right ways of doing things, you can reasonably easily plan how much time it's going to take effectively, and then stack those plans together to come up with some kind of delivery. Now, the problem with let's start with data science to begin with, because that's the basis. So data science is the art of understanding data, basically. And everybody's data is different. And even within a single company, the context of a single company, each project is different, because you're typically not working with the same data over and over again. You're working with different data every time. And that data has been produced by a domain. And in order to understand how that data was produced, you need to understand the domain as well. So there's a domain expertise there. And then there's there's an understanding of how that data represents that domain. So that's kind of like statistics. And that's different for every single project. And you need to kind of go through that pain of learning it. It's a bit like it's this kind of the same in software, really. If you come across a project for the first time, you need to understand the underlying domain in order to understand the business logic, in order to be able to write the code. It's the same deal, but it's just with fuzzy data rather than fixed rules. So that's sort of layer one. The next layer then is, okay, let's try and train a model to do something. And there's lots of different types of models you can train, but let's just pretend that we're generating a predictive model. I shouldn't use the word generating. Training a predictive model, and in that case, then you've got this other thing that sits over the top of your data. And so you're trying to massage this model, which is kind of like think of that model as like a mathematical model. Like think of F equals ma or E equals mc squared. It's that kind of thing. And the difference is that you're trying to take that mathematical model and fit it to your data. But it's not as simple as just saying fit, because there's more than one way to fit. There's lots of different potential correct answers there. So you need to tweak it, and you need to baby it, and you need to massage it until it kind of starts producing the results you want. And then RL is like a layer above that, in that not only are you trying to do that learning process, you're also trying to explore within an environment. So if you imagine like somebody who's riding a bike a lot in my book, because it's very sort of visual and everybody has done it, so they kind of understand it. If you're trying to teach an RL algorithm to ride a bike, you can imagine capturing lots of data about how the world works and building a model that predicts how you fall off a bike. It's probably a fairly simple equation, but you could probably find some data and fit a model to it. But to learn to avoid doing that, you need to actually explore within the environment. So you need to try things, which changes the underlying model. So if you sort of steer into a fall and hold your bike up, then the original model of gravity is kind of no longer true, because you're magically balancing, and you're balancing on this bike. And so you have to build another model. It has to learn another model, and so on and so forth. So there's like multiple layers of models now. And that means multiple layers of massaging and babying and teaching a baby to learn. It's the best. It's the best analogy. So it's not easy when you consider this as like an engineering discipline. We're comparing sprint one, this is 5 points, this is 6 points, we'll create this widget and that text box and this UI and it'll be great. With RL, it's like, ooh, I've got to kind of play with all these nebulous knobs and levers to kind of try and steer my baby in the right direction. And there's still kind of no guarantee that they're going to get to the end point very well. So it's hard to fit in those boxes.
And presumably this applies to also when that kind of vagueness applies to when people are building things with existing models that people have already trained. So kind of the big foundation models and things like that.
Yeah, exactly. I think it's probably a bit simpler than the RL problems that I was just describing. So you could probably treat LLMs or like language models or AI in general more like a model, in the sense that it's a fixed thing that you're playing with, but the inputs that you're passing to it do not necessarily produce the same outputs every time. And it's not just that non-determinism. It's more like it's lack of stable non-determinism that's the problem. It's like if you've got an example where you're answering a question in a chatbot, like what's the status of my order, something simple like that, then you can probably write some good tests to sort of verify that it does that okay. I think the challenge is when somebody starts typing in, like, what's the status of my shoes? Or can you tell me where my stuff is? Or things that are sort of on, like, if you were a human, you would understand that they're talking about the same sort of thing. But as an LLM, as a computer, it may not, and it may go completely off the rails there and not detect that the person's talking about orders, and therefore not querying the order service, and therefore just hallucinating something about stuff, so on and so forth.
Got you. Thinking about the different types of discipline here. So you talked about data science and kind of looking at data through the lens of the domain and understanding what insights might be there and what we can coax out of it. And then kind of machine learning to build a model that makes predictions, but based off of that data given an input. What kind of disciplines are required for different projects? If I think one of the things that for folks who don't understand everything under the tip of the AI iceberg as it's currently seen, the tip being like LLMs, they don't necessarily know at which point you can't just have a Python engineer calling a ChatGPT API, and at what point there's like you need some ML chops to actually deliver outcomes. So where's the kind of tipping point? Or is there a clear cut case where it's like for these kind of jobs, you need data scientists and machine learning folks, and for these kind of jobs, you don't?
There's maybe clear-cut lines in some cases, but in general, it's really hard. It's really fuzzy. What's your experience of dealing with people that call themselves full stack engineers? It's the same thing. Like, at what point do you need to be a back-end engineer, and what point do you need to be a database engineer? It's the same sort of fuzziness, right?
And I think, I mean, I've seen it said that there's a kind of ladder of if you're working with foundation models, things that you try, from prompt engineering, adding more things into context, using some RAG, things like that to give it more knowledge, to try and get it to do the thing that you want, then to fine tuning a thing to try and coerce it. But all of those are based on language models and also kind of knowledge and with the fine tuning, a little bit of behavior. If I had a big corpus of data in my organization, then presumably in order to get value out of that, I need to. I mean, can I stick stuff from a big database? Say a logistics company, which we may or may not have been working with recently in the last couple of weeks. Folks at Resync went and did a workshop for a logistics company. If I have a big database full of stuff and I want to predict things about how lorries are going to move, trucks for our American listeners, and when deliveries are going to be made, presumably that's not the kind of thing I can throw in an LLM because it's not really language, and then I would need something else and somebody with some machine learning background to be able to make use of
Yes, yes. I mean, that's all very nebulous. As again, like you have to go back to the original use case and the problem definition, and it's like all of these stats that you see around about X% of projects failing because of whatever, and you can apply it to any new technology. And some Harvard, MIT study will come out and give you a number saying X% of projects fail, and it's primarily because of that. They've failed because of the problem definition isn't tight enough, isn't scoped enough. But that's true of any technology. If you said to a certain rich American that we want to build something to cross an ocean, I'm sure it could come up with 10 different ways of doing that, and nine and a half of them will be crazy. So of course 95% of projects are going to fail. So yeah, if you scope it down enough, then it usually helps. It's that scoping exercise that's the hard part here, because you kind of need to understand what the different technical implementations of those look like so that you know how to slice them up, if you know what I mean. So you were right to say things like, so language models are text-based models that work really good. They work great for use cases that have text in them. So if the primary mechanism for data transfer is human text, not human text, but is text like written words, then LLMs are fantastic. But if your use case involves numbers, then it starts to get really tricky. And it can do an okay job. Quite often you can sort of delegate highly numeric tasks to other tools and then incorporate that back into an LLM. So for example, one of the common ways to do that is to delegate responsibility for that to like a database maybe, or an API. Just have an API abstraction there to do some work and allow it to call it. The classic case is the canonical case is a calculator. Like, don't allow the LLM to do calculations, just provide a calculation tool that does it for you. Things like that.
Got you. I mean, one of the things we've not mentioned so far is Winder AI, the company that you run that provides AI and ML services to people. Is there a kind of, can you think of any archetypal use cases where you would be like, that is the kind of thing that some software engineers can solve for themselves with a few API calls versus this is where you need your help? So, somebody with deep expertise and deep specialism, where's the kind of cutoff point for things that you think customers can probably handle on their own and things where it's like, yeah, you're out of your depth and you're definitely going to need more specialism there?
Same again, right? It depends on your experience. If you're a highly experienced software engineer, then you probably can handle, the use of LLMs. You can probably handle the building of applications with LLMs and the uncertainty that sort of lies within. But if you're a company that doesn't have, I speak to, so we talked about this market shift, right? And I'm speaking to a lot of companies now that don't even have an engineering department. There's no software engineers. There's no IT part of the organization. They are pure sort of boring family service businesses. They rent trucks out or whatever. They don't even have engineers. So of course they're going to need help no matter what. Whereas if you've got a really experienced engineering organization, then you probably could reach a little bit further. So I don't know. It's really hard. I think judge the yeah. If your listeners are asking that question, take a look at the maturity of your technical or engineering organization. If it's quite mature, then you can probably get quite far. But still, there's always going to be a point where you're starting to run out of knowledge and expertise. And in some cases, if you try and push on past that point, it can be expensive because you either waste time doing things that you shouldn't be doing, or will are doomed to fail, or maybe you put something into production that shouldn't be there. Yeah, so it could be costly.
Got you. And we talked about the kind of role of data scientist. What kind of things does a ML engineer do, and how is that job different from a software engineer?
So again, I think it's not a job. It's a set of skills that are commonly grouped together. I've seen, like me myself, even most of my engineers are quite happy on that boundary between data science and ML engineering. So yeah, sorry, ML engineering is a group of tasks that is involved in basically productionizing a machine learning model, a data science project into an ML model, and they that kind of skill requires more DevOpsy kind of operational skills because they need to know about containers and orchestration platforms and things like that. They're typically also responsible for the platform if you've got a platform surrounding those models. So, like if you've got something to do monitoring or observability or logging, alerting, or testing, or A/B sort of deployments and things like that, then that typically falls under them. But similarly, you might have dedicated MLOps people that focus on providing that. So these boundaries are all very fluid. Depends very much on size of the organization, the skills that they can acquire as well. It's quite hard to get individuals that are specialized to such a level where they're only working on ML engineering, for example.
Got you. So it's that kind of analogy you were making earlier with full stack engineering. It's a set of skills and technologies that somebody might have experience with that has a blurry boundary. So, they're not necessarily going to be specialists in just that small part of it. And
Yeah.
for folks that aren't familiar, and I'm a raging ignoramus myself, so I can definitely be the stand-in for the ignorant audience. A model basically is just like a function, really. It's like a big file or a big thing that you hold in memory in an app, and you poke a value in and you get a value out, and you have to wrap it in some sort of application so it can talk to the outside world and the outside world can talk to it. Is
Yep.
that about right? What does deploying one of these things and kind of taking it from being a thing running in a notebook somewhere to actually being kind of live and useful to an organization? What's involved there?
Yeah, less than you think. I think it gets a bit more. So there's two main sticking points, especially if you start talking about LLMs. The first one is, where do I store those weights? So we say the parameters of a trained model. So the numbers that represent the weights in an equation. So like what y equals mx plus c. The goal is to learn the m and the c. You store those m's and those c's in a file somewhere to be loaded later. And there's lots and lots of different opinions on where you should store them. So there's like the immutable purists that state that you should bake those weights into something that's immutable, into a container, for example. And the benefit of doing that is that at any point in the future, you can just launch that container and it's guaranteed to be in the, well, actually, no, it's not guaranteed, but it will be in roughly the same state that it was when it was running in production. So it's great for auditing, great for like disaster, like postmortems, maybe if you think your model has failed, stuff like that. But the problem with that is that you get there's quite a few inefficiencies. So the first one is that you typically have to make many copies of this container because you're shifting that container to, if you're scaling out, you're moving it to different machines. So that's one issue. Some of these models tend to be quite massive. And so that final layer of your container, which contains the weights, is also massive. And so if you need to update those weights, then it's ultimately another massive download again. Actually, that's true no matter what you do, really. So that's less of an issue. So anyway, stepping back. So you've got the purists that want immutability, but there's a lot of people that have like a centralized location which is responsible for storing like a registry of all weights, and that's very common. And the nice thing about that is that you can do an update to a model without changing the underlying container. If you're just updating the weights, if you've got like a retraining schedule or something, you can just update the weights on a daily basis and the container will automatically pick them up. So no infrastructure changes required, but you lose a little bit of that provenance. So yeah, so they're probably the two sort of key ways of doing that. The other thing that can be a challenge is that sometimes these models, like when it comes to LLMs, these models can be massive. I've been using the example of like simple equations, but if you imagine that with not just y equals mx plus c, but billions and billions and billions of copies of that kind of thing, it ends up taking a huge amount of space, hundreds and hundreds of gigabytes for a single model, and you've got all of the underlying numerical instabilities involved with that as well. So if you go from one system to another that does floating point operations in a slightly different way, you get a very, very different result because all of these errors kind of multiply. So yeah, that's a big problem. Well, not a big problem. I mean, it's a problem. Actually, being able to load and run the models is a problem because you need that much memory to be able to actually start that. So if you imagine you've got 100 gigabytes worth of weights, you need 100 gigabytes of memory, and that's just to store one copy of that. Typically, frameworks require some more room to maneuver as well. So that's a particular problem with LLMs. But yeah, I'll just pause there because I'm speaking for a long time.
Oh, no, no, that's great. I mean, people come here to listen to you, not to me prattle on. You mentioned there updating models, and we've done some work together, looking at strategic work for folks trying to figure out what to do with AI in their organization, and it kind of came up there the fact that models need to be tweaked and reviewed, and their performance continually evaluated because
Yep.
the data might change that they're acting on, and it's not just a kind of build it once and then it's going to work forever kind of thing. So fitting that into an organization might be a challenge. Can you kind of explain to folks how that update process works and why it's needed?
Yeah. So imagine a traditional CI pipeline. So let's start with a traditional sort of CI/CD pipeline where you are making a change to code. It flows through a pipeline and it ends up in deployment. There's several sort of distinct phases to that, and the phases are largely the same. So there's some kind of like build process, there's some kind of testing process, and then there's some sort of deployment process. So for the build process, that's equivalent to the retraining. So we could build an ML pipeline that automatically retrains based upon uh, a new data set or a directory or something, a path to new data or a new query maybe. And that produces an artifact. And then it needs to go through several stages of testing to make sure that it does what it's supposed to do. So testing again, same as CI/CD, and then deployment. With deployment, well, no, I was about to say it's different, but it's not really. So deployment's interesting in the sense that when you deploy an ML model, it can affect the environment in which it's in kind of quite complex ways because potentially the decisions that the model is making might change behavior. But I think that's kind of true of software as well. So you can get like advanced deployment strategies to roll out slowly to prove that the overall system is not changing too much, and over time you're just ramping up more and more and more. Kind of the same for ML as well. So I would say that in many cases the overall goals are the same. It's the technical specifics of how you would do it. So you can't test in the same way. You can't build in the same way. You almost deploy in the same way, but like I mentioned earlier, there's maybe different sort of architectural patterns that you would use to do deployment.
And the testing, that's kind of being non-deterministic, it's not as simple as just kind of pass fail, right? All the tests go green. It did exactly the same thing this time as it's always done. Therefore, we're happy. It's
Yep.
more of a probabilistic situation. Is that right?
Yeah. I think the best analogy here, if you're coming from software, is fuzzing. So you know how you can do fuzz tests in your software to test different permutations of parameters to a function. Your function might work for 99% of your inputs, but it might fail for 1% of them when it's just this edge case that you never really thought about. It's those kind of issues that exist within ML models. There's always edge cases, and those edge cases are defined by a lack of data, basically. So if you think of your ML model, or think of a large language model, actually, that's even more visual. But think of a large language model. It has this high dimensional space. So think of it as like a 3D space, but it's actually millions of or thousands of dimensions. Anyway, imagine a 3D space. And within that 3D space, there are little points of which the model has seen before. So if you go to an area of that space which is dense with points, then you can be fairly confident that you're going to get a good answer out because it's had a lot of experience of those situations. But if you go to an area that's right on the edge, that's far out there, that doesn't have many examples, its nearest examples are very far away. So it's kind of trying to like interpolate or sort of project from those points, but it'll do something, but it won't do a very good job. And so that's basically the reason why you can never have 100% on any test, because it's always possible to find a region in space that doesn't have the data, the underlying model has never seen before. And because the way in which you're describing your data with just numbers, it means that the parameter space effectively is very expressive. It's very large. It's not, yeah. So I guess an analogy might be if you had a function, imagine a function with 10,000 parameters and they're all numeric. I can probably pick one single number in one of those parameters that would break your function. So it's the same idea here. So when you're testing, generally what you want to do is you need to, again, go back to the problem definition, set some sort of bounds that you are deeming these are the situations that we need to always work in. Maybe add a second boundary, which is more like we're kind of interested in this area, but it doesn't have to be perfect. And then you write tests towards that. So you make sure that your sort of central core bound always works all of the time. It's usually the really obvious ones that it should always get right. And then some other boundary that is a little bit softer where it can get things wrong, potentially.
And that process is in the model space known as evaluating evals, right, as opposed to testing. Is that the same thing?
That's a good question. So the word there's lots of words and they're all misused and they overlap. So there's kind of testing, validation, and testing, validation, and evaluation. So typically, and in fact, in my time, about 7 or 8 years ago, the definition of validation and testing flipped. So when I'm going to get this wrong now because I've still not got it in my head. When you're training a model, you're typically training it on a subset of your data, and then you save a little bit of data to test it on because you don't want to test on the same thing that you trained on because you end up overfitting. You end up building a lookup table, and then at the end of all of that process, you used to have this validation data, this holdout data, which was left out again so that you could produce your final metrics. And that was required because the actual development process could overfit on a specific piece of test data. So there was validation there, but that at some point that got flipped. So now many people call it like validation and then test. So I don't know, whatever, but separate phases there. And then LLMs brought this idea of evaluation, which was kind of added to the end of that process so that like end users could evaluate how well their application would work with a new set of tests. So I would not get caught up on specific names for things. Just think of it as testing. It's just constant testing all the way through. It's test, 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 test. You test when you're training it. You test when you've built it. You test when you're deploying it. You just test it all the time. And each time that you're going up through that stack, typically you're kind of testing broader and broader things. So like at the lowest level, you're testing like proper ML technical metrics. But like just before deployment, You're maybe testing, like doing like API tests against your container, and you're testing that the model is still working, but you do that through the API. So it's, yeah, there's a lot of learnings that well, there's ML engineers and data scientists can learn a lot from software engineering, and the resiliency that you need to build in to your pipeline to have confidence that your application is working. But vice versa, there's also a lot that software engineers can learn from data scientists, and that it's not fixed. It's not, these tests, they will quite likely fail one time out of 10 or something like that. And so you need to start getting a bit more comfortable with a little bit of uncertainty and a little bit of fuzziness in the results. Yeah.
And I'm guessing with applications that use large language models, with the non-determinism and also the very broad range of inputs they can accept, that observability is quite important as well. Like checking that not only did it do the right thing when we built it and when we deployed it, but it's still doing the right thing now people are actually interacting with it.
Again, depends on the use case. Depends on the use case. I'm never one to say that it's always required. Even tests, right? Like when I'm writing some throwaway prototype thing, I'm not gonna be writing tests. It's the same thing. A lot of LLMs are really great at summarizing stuff, and a lot of use cases rely on asking the LLM to take this data in and produce a short, concise summary out, or even like a title or something like that. And that's the type of thing that it's kind of always going to work. And even if it doesn't work perfectly, it's still probably going to be good enough. Like I'm not going to get super mad if my Claude chat listing has a title that is not doesn't perfectly describe the content that is within that chat or something like that. So observability from that perspective is more like, does it work? Does this service that provides the titles work? And that's probably good enough. But on the flip side, if you've got an ML model that is deciding whether somebody gets accepted for a loan or not, then you absolutely need to do a shit ton of testing to make sure that you're not, well, either way, you're not rejecting people that you should be accepting or accepting people that you should be rejecting. So it's very, very use case specific. Basically, oh yeah, I should have said this at the start. It's risk driven. All of these things are risk driven. If you have a large amount of risk and a large, so if there's a large chance of something going wrong, or if there is a large chance of the implications of that, if the implications of that going wrong are really bad, then you need to do something about it. Yeah.
Yeah. Okay. We were chatting a while back about like, what does AI native mean? What is an AI native organization? Have you got any firm ideas on that? I mean, it seems to be an evolving space, right? There are new tools and techniques coming out all the time. The capabilities of, the foundational models are constantly changing, although it seems to be kind of tapering off at the moment. If somebody were to, if I were to push you to try and define what an AI native organization might be in October 2025, would you be able to give a fair stab at that?
No.
That was an
No,
excellent
I
answer.
haven't read Pinney's book yet, so let's go away, read Pinney's book, and come back to that one. No, for me, I think I mentioned earlier on, check your technical maturity, your organization's engineering maturity. I think that's a similar thing that you could do with AI. So from my perspective, AI native is less about technology and more about the organization. It's, does the organization have the maturity? I don't even like the word maturity. Does the organization have the experience to be able to execute an AI project? And that is obviously going to change depending on the specific use case. So it might be a yes for a let's use an LLM in our application, and it might be a no for let's develop an ML model. There's nuance and all of that. So I would suggest it's maybe something like that. So if you have the capacity to be able to execute on the AI projects, then you could say yes. What do you think?
That was a good move. Bit of jiu-jitsu there. Podcast jiu-jitsu. I mean, for me, I think I've been trying to identify different strands of like AI nativeness. And there's one that is quite familiar to, I think, most software engineers, which is like using AI in the development process. So you're not necessarily building something that leverages AI, but you leverage AI to build the thing. So,
Yeah.
using Claude code and this, that, and the other, and making sure that you're kind of making use of the capabilities of foundation models that are readily available in most of the aspects of your work. So at the moment, I'm working with a company building a training course for 100 developers to kind of be better at using AI coding assistants. And one of the things that occurred to me only a couple of days ago was like, hang on a minute. I get a bit fed up trying to like write bash one-liners and then going and ask Gemini. Like, there's no way I would do that when I'm writing code. Like, have a separate LLM session in a web browser and ask it questions. I'd expect it to be, in my IDE. So I was like, there must be terminal emulators that do this. And so I installed Warp the other day, which has been around for years. It used to be cool just because it was a terminal emulator in Rust, but now it's got a built-in, like it figures out whether you're trying to run a terminal command or whether you're having a conversation with it. So there's like all sorts of different ways just in software development that you could deem yourself AI native. There's the ability to create things. Thinking about the work that you and I did together, the ability to create insights from your own data using models trained on your own data that maybe you don't want to share with anyone else, and there's no existing model that can do that. That seems like a kind of deep, what's the right word? Kind of like it has inertia, right? It's not easily displaced. Like, somebody else can nick your prompts that you're sending to an LLM. But if you've got your own data and your own model trained from it, that seems like a more kind of weighty kind of thing that's harder for somebody else to steal unless they get all your data or get similar data. So there's that kind of capability, which I think is maybe where we need data scientists and machine learning folks. And then there's like maybe the other organizational parts of the organization that we tend to ignore. Like, what are people in accounts doing? What are people in marketing doing? Are they using things like ChatGPT and Gemini and all the other tools to make their jobs easier? Is there somebody running a low code platform inside the enterprise who can then go and create tactical vibe coded solutions for these people? Like, if you're not leveraging all of those capabilities that exist now because of the advent of LLMs, then are you really AI native for a definition of AI that's heavily biased towards the usage of LLMs? That was my very long attempt at answering that.
No, that's interesting. Actually, interesting for two things, because you said AI nativity at the start there. So I was just thinking like an AI Jesus, like in a crib at the
Well,
school
we are coming up to
nativity.
Christmas at this time of year. Like, somebody needs to do that, and we can have an AI
But
advent calendar to go with it.
yeah, but the second point is that you were largely talking about the use of AI in your day job. That defines the nativitiness. I'm not sure if I agree with that, because if you go back to cloud native, I think that was probably, again, Pinny's fault for coining the term. But if you go back to cloud native, I don't think that was about normal people using the cloud. It wasn't about the accountants using GCP, or I don't know, whatever the cloud is. I don't think. It was more about the technical organization doing their work in the cloud. So that's why I have this sort of view of AI native being a bit more like, it's not really about the use of AI. It's about the technical organization using AI to deliver things. But I mean, but that's not to say that all of your points are absolutely correct. The use of AI is applicable across the org.
Yeah, and I think it's an interesting point because with the whole cloud native movement, you're right. It was very much about infrastructure, and we're like, end users couldn't tell the difference. If they could tell the difference, it was ideally because their apps were more reliable. The online banking didn't go down as often, and it updated more frequently because there was more agility enabled as a result. I wonder, and so comparing this kind of wave of AI to cloud tech, like it's kind of been striking me for a while that this is maybe more close to the dot-com boom and the rise of the web, in that there are things that are user facing. If a bookshop, I mean, I used to work in a music shop as a teenager, and I remember having conversations with the guy running it, that Amazon is a thing. Can you imagine this getting better? And we were talking about building a PHP e-commerce store in 1999 and things like that. It was all very good fun. So there were these kind of mom and pop type shops and smaller businesses who needed to become like don't know what we called it then. It definitely wasn't web native, but like,
Right.
internet enabled, or e-businesses is probably what it was called. I don't know whether there's a kind of better parallel between AI and that. Maybe, I mean, this is one of the problems with the term AI. It's too broad, way too broad. It means too many things to too many people. I
Yep.
wonder if there's going to be a moment where somebody captures lightning in a bottle and kind of coins a new term that maybe just covers all of the using AI to build things, like all that technical work. And then maybe
Mm.
there'll be another term that captures, does your gran use ChatGPT to plan on holidays?
Yeah, I think we're starting to see things named like by use case. Like you sort of mentioned like the terminal assistant there, but I mean the more sort of canonical use case is the coding assistant, and I kind of call that a coding assistant. I don't call it AI. I call it a coding assistant. So maybe it's kind of going to be use case driven. Um, the terminology, which is probably better than what it is now, because it's always hard when it's
Yeah.
like technology driven.
Yeah, and I think with the broad, it would be great if the terminology refines itself, and we end up with more words to describe more specific things. Because I think although maybe we're kind of getting towards the tail end of this now, the number of CEOs who are being given the fear by investors of like, do some AI, we've got to be doing AI, everything's about AI, and then they come scrambling to folks like you and I, going, oh, I've got to do some AI, what do I do? It's like, well,
Mm,
there's lots of AI. What kind of AI would you like to? What problems do you have? How would you like the world to be better?
mm,
It's the broadness of that term, I think, has made those people's lives a lot more difficult.
mm. Yeah, agreed.
On the subject of coding assistants, you still get your hands dirty with plenty of programming. What are your weapons of choice in that arena?
Oh, great! I've just got a perfect segue now for a couple of projects that I'm working on. So yeah. Firstly, to answer your question, I use a weird concoction of Claude and Cursor, and my colleague keeps trying to persuade me to switch over to Z. That's like ZED. It's a Rust-based IDE, so it's super fast, super quick. But the ecosystem isn't quite there yet because everything is in Rust, right? So you don't have the same sort of ecosystem as like VS Code derivative things. But yeah, using Claude Code a lot, like in sort of CLI mode. I still need something visual to be able to see the work that it's doing. So I still need an IDE. And also a couple of things that I have noticed, and here comes the segue. One of the things, have you ever noticed that when you're using a coding assistant, that when you need it to work with another application in your organization, it has no knowledge of that other service or that other thing or that other application. Well, think no longer because this is turning into a really bad US commercial, isn't it? So I'm working on a project at the moment called Code It, and it's under the Helix banner. I'll talk more about that in a second. That's another one of my businesses that I'm running with some friends. Code It is a think of it as a code indexing server. So basically, you pop in all of your repositories, public or private, that your company is using, and Codeit will go away and index all of those things. And then when you come to a coding task, you connect your coding assistant to that indexed server, and it gives you all sorts of information about all of those different repos, depending on the task that you are doing. So probably one of the simplest examples is something like if you're writing some new code to connect securely using some sort of authentication pattern to some other server, it won't know what that pattern is. But with Codeit, it's already got that indexed, it knows exactly where to find it. It just passes along some information about that other repo, and your coding agent can succeed. So check that out if you have that kind of problem. There's also another project I want to talk about, which my colleague is working on, which is way more crazy. He has this really cool idea that he thinks that coding sessions should be and will always be in the future in remote sessions, so not on your device at all. And so what we're creating is a new service that's part of helix.ml called Helix Code. And it allows you to run remote VDI sessions in a remote server. So you get a full desktop with a full IDE, with a full coding assistant running in the background, and you run all of your coding tasks in that system, and then you hop back out in your browser and you can see them all doing their thing and moving about. And then we're starting to sort of stumble, we're starting to hit like I think what is quite a new paradigm, and it's asking the question of what's the best way of managing remote coding sessions? Like, how do you manage what they're doing? And it's actually turns out to be very similar to how do you manage a team. So how do you manage a team at the moment? You manage it with a backlog, with Kanban or something like that. So we're trying to come up with some quite novel ways of managing these coding assistants that look a bit like a backlog with Kanban, but except the Kanban isn't just like a ticket. It's actually a little video of the coding assistant doing its job. And when it's finished, it moves itself to done and stuff like that. And the real beauty, I mean, one of the main beauties for me of that paradigm is that I can finally code from the bath effectively and not risk my dropping my laptop in the water. I can just, play with my phone, which is a bit more waterproof. But yeah,
Yeah, and the
I think it's quite a new it's a new paradigm of doing work, and so it's going to be interesting to see how people play with it.
Yeah, I mean, there's quite a few interesting things there. I mean, one thing that is in my head that I should definitely stress when you're talking about connecting to VDIs, running coding sessions, I should stress that this is also your same friend that recommended Z because it's written in Rust. So he's got a
Yeah,
very low tolerance for latency. So it's not going to be like working in a horrific enterprise bank where you connect some under provisioned VDI over a really shonky network. The managing multiple agents thing is I mean, that seems to be the way that it leads to. Some of the more experienced folks I know that have been playing with Claude Code for a very long time are managing multiple agents. And I spoke to somebody last week, a couple of weeks ago, who was doing that quite successfully. And their pattern of usage was multiple Git work trees, and they were doing the back end with one agent instance, the front end with another, and then maybe a different approach to the front end with another agent, all on the same story. And that seemed to work quite well for them. But then I spoke to someone, I don't know whether we've talked about this publicly, so I won't name names, but somebody who their most AI kind of enthusiastic developer was knocking it out of the park for 3 or 4 months, being 10 times more productive than they'd been before using Claude Code and multiple instances thereof. But they were working on multiple stories at once. So they were constantly mentally context switching between these different tracks, and eventually ended up with burnout, and I had to take some time off work. And I'm
yeah,
like, I can totally imagine that, like how hard that would be. So trying to find ways to manage multiple instances running at once is definitely, I think, a problem that needs solving in our near future. You mentioned Helix, and it's probably good to tell the folks that you can do another one of your American style advertisements where you say the same thing 3 times and talk about a value. Have you got any are there any vouchers for Helix you can give away?
absolutely. Yeah. Have you ever worried about your data going missing? So no, we started Helix with the premise that there are companies out there that for privacy reasons or security reasons, you need to run everything in an enclave, in a separate in a private cloud, or quite often on premise, and that's because of worries about data breaches or potentially the loss of code or data by using a third party service. So there are many companies like that. And yeah, we kind of specialize in helping them by deploying Helix, which is an on premise AI platform, and it helps those companies use AI without the risk of losing or sending their data to somebody they shouldn't be.
So it's kind of like self-hosted AI in a box. Is that
Correct.
how an idiot like me would describe it?
Yes, yes, correct. To the
Cool.
to the to the statement, not the idiot part.
Well, yeah. Cool. So, and Helix doesn't just like it's kind of turning into a bit of a platform, isn't it? Like you can run things on it. It's not just for running, hosting models, is it? Aren't there kind of like agenty things and kind of coding-y things that are part of it?
Correct. Yeah, we're very much at danger of expanding the scope too much. So yeah,
Is this
we went
because
down.
Luke gets bored and has too many crazy ideas?
Exactly. But they're all good ideas. It's just we've got to find the right combination that stick. So yeah, the core problem and the core requirement, and this is built up over time. It's not like we're just trying to do all things at once. The core requirement is that you can host. So that's kind of what we tackle first. And so you can just use it like you would an OpenAI API endpoint or something like that. Um, and that was the base of it. But then we were like, well, what do we do next? And so we started playing with like different RAG implementations. We did probably one of the I don't know. I don't know. call it world first, but it was certainly probably one of the earliest platforms to integrate Vision RAG into their solution. So that's really cool, where instead of using text to search through documents, you can use images. And so the way that it works is that instead of indexing text like you would with traditional RAG, you would index images through a vision embedding model. And then when the user says, I was interested in the price of the stock ABC123 the other day. And buried deep within a PDF somewhere, there's maybe a graph or like a plot of the stock price or something over time, and it would learn to be able to pull out that graph and answer the the question from the graph rather than actually getting it from text. So that can be useful in some domains. So yeah, we've got a whole sort of RAG story in there for integrating all of your information. And then we moved on to agents, and we've gone down quite an interesting route. I think it's interesting, but it's interesting that not many other people have gone down this route. So if you look at other agent providers, there's generally sort of two types. There's like the super user friendly type, where there's zero configurability, and they're basically just chatbots basically. And you can connect them to a phone system, or you can connect them to various different things, but it's all done in a very tightly controlled way. Then you've got like another paradigm where you've got like the sort of drag and drop, like workflow builder type tools, where you can kind of build agents from them as well. It gives you a little bit more flexibility, but still it's still not very developer friendly. And then all the way on the other end of the spectrum, you've got the coding frameworks. You've got the coding frameworks coming from Hugging Face or LangChain, or all of these types of things. And we sort of sit somewhere in the middle, where our agents are by configuration. They're kind of like configuration driven agents, and you attach things to the configuration and treat them a little bit like code, basically, but in a higher level kind of YAML format. We kind of sit in the middle, and so it works well from a resiliency perspective, because it's very kind of like GitOpsy, but it remains to be seen whether it sort of gains adoption over one of these two approaches. And then yeah, finally, with some of our clients, like, yes, they've got agentic use cases, yes, they need to use private LLMs, but actually number one use case really is writing code. And so started sort of diving into this paradigm of writing code with agents, and that's what led us down the Helix code path.
Cool. Going back to the side project yours, a code something, what was it called again?
The code indexing server, Codit.
Yeah. Code it. It's interesting that you worked on that, because it's when you see a pattern of several different solutions, you kind of realize that there's definitely a problem there. And it reminds me of a couple of things. So I've been kicking the tires on Context 7, which I gather kind of summarizes the documentation of libraries that you may want to use. Tessel have a kind of tool and an ecosystem that will look at open source projects, generate kind of agent-friendly summaries of the code, and then make that available so it can look at your dependency management tool and go, oh, you're using version 1.3.2 of such and such. I'll go and pull out the kind of agent-friendly markdown documentation written by Tessel for that. And presumably yours is looking more at the code. So you're kind of doing like code rag of pulling out bits of pulling out functions and methods that might be relevant to the user's current context.
Yeah. So yeah, you're right to bring them up, and I think what I'm trying to do with Codit is do all of those things and more. So it's not different. It's just they're just more of the same things. And actually, we've got just a massive list of potential ideas. So you've already mentioned one is indexing the documentation. One of the biggest problems that we see in enterprise is that there is no documentation.
Yes.
Quite often, what we have to do is one of the last. I call them enrichments. So basically, the source is the code, and I'm deriving all sorts of different things purely from the code. And the first one was this idea that I called a snippet, which was a piece of code that sort of typifies the use of a particular bit of the program. And that works in some cases, but it doesn't work in others. In use cases where it's very much, I am a user of a library, that doesn't work so well, because the actual code in a library doesn't usually represent how you're supposed to use that library very well. So quickly realized that we needed more enrichments. We needed different types. So I've just worked on one, which is the public API documentation. So it again goes through all the code, extracts all the public methods and public classes and stuff. But instead of purely relying on the poorly documented code that is already there, we've got an LLM. Let's ask the LLM to generate the documentation for it. So we actually inject that into there, and so on and so forth. And we've got loads of plans for like more architecture type documentation. So a lot of projects that we develop ourselves um, struggle a little bit, even when you're within the same repository, because it doesn't understand the overall architecture. So to give you an example, Helix itself, the physical architecture, it consists of like a centralized kind of control plane, and then lots of little runners that connect to it. But the when you're coding in the coding agent, in the coding assistant, sorry, with writing Helix code, it doesn't appreciate that it's actually the runner that connects to it and naturally writes code that is wrong. It just won't work because that's not how the physical architecture of the system is. So yeah, so by providing it with the ability to extract some architecture documentation, then that helps with that. So yeah, we've got a full list of enrichments that I'm just slogging through at the moment. So yes, hopefully text documentation, architecture documentation, and everything else in between.
I quite like that idea of, I can understand why it wouldn't work when you're consuming somebody else's library, but being able to say that like this function over here or this file, this is how we want to do it. This typifies the coding style that we want. If you're going to write code like anything, try and write it like these functions that were written by our best engineer last week, rather than by somebody that we outsourced it to 4 years ago that's in some other file over there.
Yeah, that's exactly right. Actually, one of our customers even suggested adding that as a filter to all of this search functionality. Like filter it by the person that actually did the commit, because
Mm.
some of those are better than others. I'm
Oh,
not
crikey,
sure how
yeah.
you would do that, but yeah, you'd need to start ranking developers according to their quality of code.
I'm pretty sure German employment law would have something to say about that. Cool. Right. Well, we've done about an hour of waffling on.
Okay.
Is there anything else that you particularly wanted to talk about? Well, I think we've plugged most of the things.
Oh
We've
yeah,
mentioned the
plugged
book,
all
we've
the
mentioned
things.
Helix, we've mentioned the side project, we've mentioned Winder AI.
Yeah, yeah. Thank you for that. Appreciate it. What else would I like to talk about? Oh, let's maybe talk a little bit more about RL, because I think that's probably
Yes.
unique compared to other people that you've spoken to in the past.
Yes. In fact, I think it would be good to understand a bit more about RL and what makes it special. And so I don't forget, I'm going to mention this now. I would be interested in your take after we've talked about, what you want to talk about at RL, how kind of modern iteration of prompts starts approaching something like RL, reinforcement learning. Like we're kind of getting some kind of meta RL thing where you built an application, it uses some prompts, it tries to achieve an outcome. You then tweak the prompt, see whether it achieves the outcome better. It's sort of like reinforcement learning where it's, trying to find its way towards an ideal outcome. But that's for later. So say what you were going to say before I started using you as a memory aid.
No, that's okay. I think we can maybe drive it in that direction. So reinforcement learning is different. It is a different paradigm compared to machine learning for two reasons. The first one is this idea of exploration, exploring within a space and giving an agent agency to be able to do that exploration. That's why we use the word agent in LLMs. It came from reinforcement learning because it has agency. So that's one aspect. The other aspect is the definition of success, the definition of a reward signal. And it's much more liberal. It's much broader than you can use in traditional machine learning paradigms. So yeah, let me maybe just step back a little bit and recap what reinforcement learning is again, and actually describe the hardest bit about it. So reinforcement learning is the mathematical codification of a while loop, basically. And this while loop has a couple of things going around in it. It has, probably the best word is observations. So it has a set of observations about the world around it in the environment it's currently running in. Then it can suggest actions within that environment, which changes the environment. And then there's a reward signal to direct it in a certain direction. So observations, actions, rewards. And the agent keeps going round and round and round and round until it maximizes that reward signal to some little definition of success. So the way in which you would practically apply that is that you need an environment to operate in. And this is actually the number one challenge in all RL projects. And um, this is why it's still hard. And it's because in order to do that exploration, you either need to do it in real life or you need to have a really, really good simulation that emulates real life. And so that's fine in some domains. So if you're in like online advertising or something, or if you're in web hosting, you get bazillions of clicks every day. It's very easy to test and experiment in production. It might affect your top line figures a little bit, but it's okay to experiment because there's no sort of dramatic like loss if somebody happens to get a bad suggestion once every while. Whereas if you're working on an industrial pipeline, and which we have done, and you are attempting to control an industrial process, then actually allowing an agent to learn from scratch and predict the position of a valve could be catastrophic. It could cause an explosion. So you just can't do it. And that's where you need a simulation. But the problem is that the fidelity of that simulation, if it's not perfect, then even if you're doing well in that simulation, when you go into real life, you still don't really know how good it is. So you end up with all these sort of proxy definitions of evaluation that kind of like poke it in different ways to see how it might go wrong when you go into production, and you just try and minimize those as much as possible. And then when you are finally in production, then you can really start the real job of learning. So you go through these several different phases, and they're all quite tricky. Um, uh, and it's predominantly because ultimately you need to do this in real life, and quite often you can't. So yeah, so bringing it back to so let me just say it's not all bad news. There's a new paradigm that came out after the book, or it didn't come out after the book, but it started to become more popular after I wrote the book, and that's offline reinforcement learning, and that's basically doing RL but from logged data. That really, really, really helps because it kind of alleviates the need for a simulation as much, because you can learn good policies and good strategies purely from offline data.
So how does that kind of logged data work? So I can imagine how the building the kind of model simulation environment. I shouldn't have used the word model there, definitely overloading a term, but the simulation environment works. Like I've seen videos on YouTube of like reinforcement learning how to drive cars around a 2D racing game and those
Yep.
sorts of things, where the game and its physics and the boundaries of the track are like the environment. How does that work with the offline stuff and the logged data?
So it works exactly the same. So there's an algorithm called behavior cloning, which is the simplest algorithm to imagine, and the goal there is to learn an agent that is capable of doing the same things that an expert would do, a human would do. If you imagine that the human had generated this offline data, and the way it does that is that you have a vision, you have the action that was produced by that human, and so we're trying to train the policy, which is the underlying algorithm inside the agent. We're trying to train the agent to do the same thing. And whilst it doesn't do the same thing, then penalize it. And then you just use normal ML like techniques to kind of nudge the weight so that it produces more of those actions that look like those actions. And then you keep going around in that loop over your entire data set, and you do it more and more and more and more. And eventually you kind of overfit the data. You kind of learn exactly to predict the same action that was generated in that offline. So that's kind of the basis of it, and you end up with strategies that look like human strategies. The really cool bit is that we didn't really talk about the reward much there. So quite often in offline data, you also have some sense of reward. So we're working with one client at the moment on revenue management. And so if you imagine now you've got some offline data where you have an observation of something, doesn't really matter what, you have an action that was chosen by some real person, but you also have the outcome. And that, say the outcome was like, that made 100 sales or something like that. We can use that number as the reward in our reward model. And now it's not quite learning what the human did. It's learning what the human did in combination with the reward that it produced. And so you actually get like the best possible outcome by observing the best possible outcomes and kind of learning mostly from them and disregarding all of the less positive outcomes. So you end up with a set of strategies that are based upon your offline data, like the best you could do. It's like taking the best part of that data and using that to power your future model. So that allows you to get, yeah, really good results without even touching a simulator or real life at all. Now, the obvious caveat with all of that is just like in ML, it can only learn from the data that it has observed. So if it hasn't observed a part of the space that might exist in real life, then the strategies are probably not going to deal very well with that particular thing. So it doesn't get rid of the need for learning in an online sense, learning from real life. Also, simulators are still helpful if you still have them, because you can go through like offline learning, simulator learning, and then real life learning as well. It's like different stages you can do to kind of fill out some of those gaps.
And what kind of problems is reinforcement learning most suited towards? Because presumably an LLM is going to be no use to me if I want to work out how to most efficiently run my estate of HVAC and refrigeration equipment.
Yeah, it's tricky because it's quite widely applicable, but it's quite challenging to apply because of this requirement to eventually learn in production. So, I mean, it can be applied anywhere where you can see we need to optimally learn some kind of strategy. And I think strategy is the best sort of description of what RL does. It's not a technical term; it's the word that I use. But anywhere where you have a set of strategies that optimize for the thing of interest. And so it could be anything from, yeah, controlling temperature units to managing a football team to setting prices. You know, all these things require some kind of background strategy in order to do them effectively. And it's those learned strategies. It's those strategies learned from experience. That's the perfect use case for RL.
And am I correct in thinking that a differentiator here is that a reinforcement learning system continues learning when it's in production?
It can do, but I mean, obviously, you need to. It's like any ML can be the same, but you need to connect the loop back to wherever you started your training from. So, I mean, in most production RL scenarios, they don't connect it directly back and allow it to learn online. It's more like let's just connect it back to an offline log and then update the offline log again and then put that in production and so on and so forth. But I mean, it's not that you can't do that. It's just that you're adding a potential source of instability to your system. In general, unless it's really important to to learn as fast as possible. To say that if you're in like a high frequency trading environment, for example, if your agent learns if your agent has the opportunity to learn some signal, then it's vitally important that they learn that as soon as possible so they can exploit it. Because if you don't, that edge will be gone in 10 minutes. So in cases like that, you may run in learning in production. But in the vast majority of like normal use cases, we sort of do it at a much slower cadence just to sort of preserve stability in the whole system.
Got you. And so, kind of bring it back to that point about sort of wider loops of reinforcement learning crossed with machine learning, with LLM type applications. If I have a chatbot that maybe does customer service and I get a rating at the end of that conversation of like, how much did you enjoy this customer service conversation? If that was, could that then be tied into kind of tweaking prompts? Would that be like a combination of reinforcement learning with an LLM application where it's like we tweak the prompt to nudge it towards things that have more satisfactory outcomes for users?
Yeah, exactly. Yeah, you're exactly right. So the reinforcement learning actually powers a lot of the training of these LLMs. So initially they are trained upon just like a corpus of internet data, and they are trained to predict the next word in that internet data. And that kind of fills out all of this high dimensional space that I was talking about. But it's not actually the way that people use these models. They use them by chatting with them, by instructing them to do something. So they go through a secondary round of training to uh, to 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 start to mimic how people expect these models to operate. And the way in which they do that is they have an input that is a request, they have an output that is expected, and then some kind of score of that output. And so this is the same thing again. This is the observation, the action, the reward. So we can use reinforcement learning here to fine tune or train that model a little bit more, and it will change the underlying weights of that model and nudge those weights towards providing these interactions. So you can use that yourself. So if you've got a feedback mechanism, which I recommend you do for your LLM powered application, you can fine tune your LLM on the feedback that you receive to learn a better model. And if you learn a better model, then people have a better experience and then you have a better product. But actually, the number one use case of fine tuning is when you're working, when you have a use case that is running at massive scale and it's using an LLM to do something. And the reason for doing that is speed and latency. So you can use a really big model like an OpenAI, an Anthropic, etc. model to do vast array of things, but they're really slow and they're really expensive. The vast majority of large scale use cases are quite generic. It's the same thing over and over again. It's like, trying to detect the sentiment of a piece of text or trying to summarize a piece of code or something quite generic that happens over and over and over again. So what you can do in those cases is you can train a very small language model and then you can fine tune that small language model to do it as well as the big language models. So you get all of the power and the capability of a big language model like output, but at 1% of the cost or 1% of the latency or whatever. So that's actually the number one use case for fine tuning.
Yeah, and that kind of brings me to a thought that I had earlier based on a conversation I was having at the London Agentic and MCP meetup last week, which was really good. If you're in London, then definitely recommend attending. That was a really nice set of technical talks. But where my ex-colleague Martin was showing me on his shiny 48 gigabyte MacBook Pro various smaller models running in the browser using WebGPU to run inference basically on his local device. I wonder if, I kind of feel a little bit like at the moment where we've got these massive models running in massive data centers and everyone's like, well, that's, of course they've got to be there because they're crazy expensive and the huge amounts of GPUs in there, whether that's a bit like people in the 70s going, well, no one will have a computer on their desktop because they're massive and they take up a whole room. Yeah, I did see somebody on LinkedIn suggesting that maybe Apple have seen this coming and that's why they're kind of pushing into faster memory bandwidth and more RAM in their consumer devices, because maybe we'll end up with more and more kind of local inference being done.
Yeah, definitely. And there's all sorts of things you can do to squeeze them into smaller devices. Even phones now can run some models. Phones are quite beefy computational devices, and they're already running low level tasks in there. So yeah, definitely, I think that's a thing for doing it. But I think what you've got to remember is from an engineering perspective, like go back to the problem definition again. The reason why these models in the cloud are so massive is because they need to be able to handle all tasks every day with the same model effectively. I know there's hidden routing and stuff, but whether it's me coding or my daughter being helped with her homework, the model has still got to work just as well. And so it basically has to learn the breadth of human knowledge. It's very, 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 very rare that as engineers, we have a use case that is that broad. It's usually many orders of magnitude narrowed in scope. And when it is, equivalently, you should be able to get away with a model that is many orders of magnitude smaller.
Cool.
So I think if you think of it like that, then yeah.
Yeah, that makes sense. Kind of it's cutting off slivers of the big models into sizes that will fit on a laptop or whatever. We are at an hour and 20 minutes, and we're also like, of the 90 minutes of your day that you pledged to give me, we're pretty much up for that. I think we've done all the plugging. Do you get any significant, I shouldn't ask you whether you get significant royalties from the book. That's probably not appropriate for a public broadcast. But if you're interested in reinforcement learning, then go and have a look at the O'Reilly book by Dr. Phil Winder. I haven't called you Dr. Phil yet so far on this podcast, I don't think. And otherwise, if you need help with AI and reinforcement learning and machine learning type stuff, have a look at Winder AI. And if you want to run an AI in a box on premises, then have a look at Helix ML.
Yeah, thanks for that, TJ. Lots of hands in many pies.
Cool, right. Thank you very much, Phil.
Cheers.
Thank you very much to Dr. Phil there for joining me for that chat. If you have any feedback on the Waves of Innovation podcast, it'd be really great to hear from you. If you could email wavesofinnovation@resync.com, that's re-cinq.com. We'd be grateful to have your feedback. It'd be good to hear what you'd like to hear more of, what you didn't like, what you'd like to see in the future, that kind of thing. Also, check out the recent website. It's recently been revamped with more content. And if you are in need of things like AI workshops or want to attend any of our upcoming webinars, then please do check it out. Hopefully, you enjoyed that and you'll hear me in the next one.